Hi everyone, in this video I will be discussing the use of the electrochemical series to predict spontaneous redox reactions and the operation of galvanic cells. So this is just a quick recap of what we did last lesson. We tried to build this electrochemical series, or the first three entries of the series anyway, using a copper hydrogen galvanic cell as well as a hydrogen zinc galvanic cell, and we list every half cell as a reduction half equation. So you have the oxidizing agent on the left and the reducing agent on the right, and the order of the half equations depend on which half cell undergoes reduction when you make the galvanic cell. So the higher equation would belong to the substance which undergoes reduction. Now, from that idea, essentially what we do is we can run a galvanic cell between the hydrogen standard electrode and any other half cell that you can build. And then with that, you're going to be able to generate this, which is the electrochemical series. Now, this is not the exhaustive list. The actual series runs for much longer than this, but this is the one that you will get in VCE. And I do suggest that you have an actual copy of this so then all the annotations are a little bit bigger so you can see things a little bit more clearly, but this is the whole series. So in terms of the features of the series, the first one, which I already mentioned, is that each row lists a reduction half equation between an oxidizing agent and its conjugate reducing agent. So all the reactants or all the species on the left column or the left side of the equation would be oxidizing agents. So everything in blue here would be oxidizing agents, and all of the products or all of the species on the right column would be reducing agent. So everything on the right would be reducing agents. So everything on the left is oxidizing agent and everything on the right would be reducing agent. Now you can see this row, which is 0.00, and this is your hydrogen electrode. And from the hydrogen electrode at 0.00, you can assign what is called standard electrode potential for all of the other half cell, depending on the voltage that is met between that half cell and hydrogen, and whether that half cell was the cathode or the anode compared to hydrogen. So that's the electrode potential, and in this particular version of the electrochemical series, all of your half equations are measured and ordered from the highest standard electrode potential to the lowest. All right, so those are the key features: left column, right column, electrode potential. Let's use that to answer example 1. Which of the following substances can act as oxidizing agents? So the main thing here is you need to be familiar with the electrochemical series, and it's going to take time for you to know where everything is, but you get better with practice, and it actually doesn't require a lot of practice to be very good at this. So if the question asks you which of the following can act as oxidizing agents, all you need to do is to see which of these species actually appear on the left side of the electrochemical series. If it appears on the left side, it can act as oxidizing agents. So I'm going to start with H2O. So you just need to find out, you'll be able to find H2O here. So H2O can act as an oxidizing agent. Manganese, now manganese is actually only on the right side, so manganese will not work. So H2O, yes. Manganese, no. And the next one I need to find is gold iron, which is up here. So Ag plus, yes, can act as an oxidizing agent. Fe2 plus. Now Fe2 plus is interesting. You actually will see two Fe2 plus present. So this is one of the species that can act as both an oxidizing agent and a reducing agent, but it does appear on the left side of the column, so it can be an oxidizing agent. Lithium. So lithium is down here. So no, you're not going to be able to find lithium anywhere else. Chlorine gas is up here. So yes, it can act as an oxidizing agent. And fluoride ion is up here. So no, because it's only on the right side. So any species that appears on the left side of the column can act as an oxidizing agent. And that's all you need to do for example 1. All right, the next features of the electrochemical series has to do with the strength of the oxidizing agents and reducing agents. And this comes out of the fact that you always put the half cell that undergoes reduction on top. So the higher half cell is the one that can undergo more reduction. So if you go up the series, the strength of oxidizing agents would increase. So if you go up, there is an increase in oxidizing agent strength. which means that the higher an oxidizing agent is, the stronger it is. Another way to remember it is that top left, so F2, fluorine gas, is the strongest oxidizing agent. And I think this aligns with the fact that fluorine as an element is extremely electronegative, so it really wants to gain electrons. That's the definition of electronegativity. Therefore, fluorine gas is also a very strong oxidizing agent, since oxidizing agents also gain electrons. Now, on the other side, if you go down the series, the strength of reducing agents increases. So if you go down, the lower a species is on the right, the stronger is its reducing power or its ability to act as a reducing agent. And the bottom right substance, or lithium, it's going to be the strongest reducing agent. So the two strongest species are in the top left and in the bottom right. And I think this also hopefully makes a little bit of sense to you. Lithium is used a lot in batteries, and one of the reasons for that is because it is a very strong reducing agent, so you can generate a lot of voltage out of the battery. The other reason is that it's a very light metal, so you can use it in portable devices. So that's the second feature. Top left, bottom right are the two strongest oxidizing and reducing agents. So by finding the positions of a substance, you should be able to compare the strength of oxidizing agents and reducing agents. Okay, so let's have a look at example 2. You need to identify the strongest oxidizing agents present in the following. So once again, I have some species here. And because we're talking about oxidizing agents, I'm just going to highlight species on the left side of the column. So we have copper ion, so Cu2 plus is here. The next one is nickel, which is here, and then we have chlorine gas. H2O, you will see that there are multiple H2O present, but since we are looking at oxidizing agent, I'm just going to highlight the one on the left, and Sn2 plus. So this is Sn2 plus. So the strongest oxidizing agent must be the highest one, so it's going to be chlorine gas. Okay. And then we need to identify the strongest reducing agent in the following. So we're looking at reducing agents now. So I'm looking at everything on the right. Maybe I should just change the highlighting color. So let's go with everything on the right. So we have cadmium or Cd. So that's cadmium. Fe2 plus. Fe2 plus on the right is up here. Tin 2 plus on the right is here. Lead Pb is lead even in here? Oh yes, H2 gas, so right above it, and H2O is here. There's actually two. So we're looking at the strongest reducing agent, which will be the species that is the lowest on the right. So in this case, cadmium. Okay, so that's very simple. Just make sure that you highlight the correct species and you should be able to do the comparison. This is my advice, and I do this every year, is if you want, because you're going to have to use electrochemical series a lot and you're probably going to have to highlight a lot, you can either laminate the series or you can just put in a plastic pocket and then highlight on top of it. As long as you wipe it out straight away, it's not going to stain. My unscientific experiment has confirmed that orange is the color that removes the easiest. Okay, so that's the second feature. Now, the last thing is, once you know the order of the oxidizing reducing agents, the most important use of the electrochemical series is that you can use it to predict if a spontaneous redox reaction will occur. Which is another way of saying is that you can predict whether or not if I mix two species together, a reaction will happen, given that that reaction is redox, of course. In general, the rule here is, first of all, only the strongest oxidizing and reducing agents present can potentially react, kind of like a survival of the fittest type of thing. So only the strongest oxidizing reducing agents present can react. And I say potentially react because they may not react. The second condition has to be fulfilled as well. A spontaneous redox reaction will occur if the strongest oxidizing and reducing agents present form a backward Z. Right? Now, backward Z is basically like this. I probably want to go back to the pen for now. So a backward Z is like this, yeah? Or you can say a negative gradient in the electrochemical series. In other words, the oxidizing agent must be placed above the reducing agent if you want a spontaneous reaction. Okay, so what do I mean by that? Let's go through a few examples. So this is example, well, the first example. Predict if a spontaneous reaction will occur in each of the following situations. That should say an S. Anyway, the first situation is you have some iron and you're going to place it in a solution of hydrochloric acid. So if you want to use the electrochemical series to approach these kind of questions, there are a few steps that I've listed here. And once you get very good, you can do a lot of these steps in your head. So step one is to list all of the species present. A lot of the time students skip this step, and eventually, like especially in year 12, it's normally gonna not end well because you're going to miss one thing that's also present that causes the reaction. So we're going to read the question carefully and list all of the species present. So Fe is present, Fe solid. Now if it's say, so HCl, because hydrochloric acid is a strong acid that fully ionizes, there are two things that are also present, which is H plus and Cl minus. So if anything that will exist as ions, you actually want to write the ions out and not HCl, because you're not going to find HCl on this electrochemical series, but you will find H plus and Cl minus. And the last thing that is present is water, because this is a solution, so H2O is also present. So there are essentially four things present here: Fe, hydrogen, ions, chloride ion, and water. All right, step two, highlight all of the species present on the electrochemical series. So I'm going to do my highlighting again. So we have Fe, and the key is you want to make sure that you highlight just the species and not the entire, not the entire half equation. So I need to actually change the highlight first. Okay, so we have Fe present, so that's Fe. That's a terrible highlight. Fe, and then we have H plus, which is here. Cl minus is up here. And I'm going to highlight every single H2O that I can find. So there is H2O here, there's H2O here. I'm not going to highlight this one because this is not just H2O, it's H2O and oxygen gas. And I know there is oxygen in the air, but the amount tends to be too small for a reaction to actually occur. So unless you have pure oxygen present, I'm not going to highlight this one. I will, however, highlight this H2O, which is at the bottom. Okay, so that's everything that's present. Step three is to circle the strongest oxidizing and reducing agent present. So this is where the comparison that we discussed earlier comes in. If you look at the left, there are two oxidizing agents present, hydrogen ions and water, but hydrogen ion is higher, so this is the stronger oxidizing agent. If you look at the right, there are four reducing agents present. The lowest one is going to be the strongest. So these two are the strongest oxidizing and reducing agent present. If there is a spontaneous reaction, it has to occur between these two species. And step four is to connect the strongest oxidizing and reducing agent present. Okay, if a backward Z can be formed. Now, a backward Z means that if I just continue going this way, you're going to get your backward Z. Or you can just see if there is a negative gradient, then a spontaneous reaction can occur. And because I can achieve that here, the answer is yes, there is a spontaneous reaction. Okay, so that's the first example. Let's move on to another one. So I have copper being exposed to air and water. All right. I think that I'm going to assume that the air here means oxygen. I know it doesn't. Okay. So that's just me being. Let's just start with listing all the species present. So copper, it should really say pure oxygen. I know I'm like eating my words here, but I'm gonna change this to pure oxygen in the question so that is clear, and I will not do this to you in your sack. So let's say it's exposed to pure oxygen and H2O. So there are three species present: copper, oxygen, and water. All right, let's just put the H2O up here so we can see the instructions. So step two is to highlight all the species present on the electrochemical series. So copper is here. There are multiple H2O, 1, 2, 3, and oxygen. Now this one is actually very interesting. You can highlight this one, because there is oxygen and water present. I'm not going to highlight that oxygen because I don't think H plus is present here. So this is actually what I have. So you can have two species acting as the oxidizing agent. It's really just the oxygen, but because water is present, I can highlight it too. Okay, I'm not supposed to. Let's go back to the pen. Step 3 is to circle the strongest oxidizing reducing agent present. So once again, if you consider the species on the left side of the series, O2 and H2O is the highest, so it's going to be the strongest species here. And on the right, it's going to be copper, which is the lowest out of all the species on the right. And then I'm going to connect them. You're going to have a reaction, not a very significant one, but there is a reaction here. This is a negative gradient. You can form a backward Z. So the answer for B is also yes. Okay. Let's do one more. Sodium is placed in some water. Now you should know that there is a spontaneous reaction occurring in this case. You've seen this demonstration multiple times. But let's just follow the step. There are only two things present, sodium and H2O. So that's step 1, and then I'm going to highlight as well. Okay, so I have sodium down here, and then I would have multiple H2O. This is not water, by the way. Did I highlight it earlier? Oh, what is this? Okay, I did not highlight hydrogen peroxide by accident. This is just another section of the series. I think I've shifted up a little bit. So we have two water and we have sodium. I didn't even show the other H2O, which is always the weaker species anyway, so it's not going to react. And then circle the strongest oxidizing and reducing agent present. So there's only one oxidizing agent present, and the sodium is a stronger one. So you can clearly see that I can form a negative gradient between the two, or a backward Z. So there is a spontaneous reaction, and you have seen this demonstration. It's a pretty violent reaction, actually. Let's do this one. I hope I actually include an example that doesn't have a reaction, but it doesn't look like it. So zinc chloride solution. Now, zinc chloride solution contains zinc ions, chloride ions, and H2O. Three species already. It's stored in an iron container. I feel like the question is almost telling you that there wouldn't be a reaction. Like, otherwise, why would you store it in an iron container? Anyway, don't quote me on it because I don't remember what the answer was supposed to be. So there are four things present here. I'm going to highlight all of the species on the electrochemical series. So we have water and then another water. That's not a water. Zinc 2 plus is here, and chloride ion is here, and Fe is here. Okay, so that's everything. Let's circle the strongest oxidizing and reducing agent present. There's only one. Oh, sorry, I forgot to highlight the other water. Let me go back and do that. Just right underneath the zinc ion. So there are two oxidizing agents present, but the zinc ion is a stronger one. So I'm just going to circle that. And there are four reducing agents present. Fe is a stronger one, so you have that. However, you don't have a negative gradient when you connect these two, so you don't have a spontaneous reaction. So just go with no. Oh, we're not done? Oh, okay, we're done. This is another type of question. So there is a spontaneous redox reaction already, but you need to write the half equations and the overall equation for the reaction that occurs. So this is another function of the electrochemical series. Not only does it tell you that a spontaneous reaction will happen, you can also use it to determine exactly what the equations will look like. So let's start with some magnesium being placed in a hydrochloric acid solution. You've seen this reaction, you actually know what the products are, but see whether we can derive it from the electrochemical series. I'm going to follow the steps again, so list everything that's present. So this is magnesium, H plus, Cl minus, and water. So there are four species present. I'm going to highlight the species. So we have, did I not include magnesium in my list? Oh, isn't that great? So there is supposed to be magnesium somewhere down here. So let's just use your imagination and assume that there is a magnesium, which I think is actually underneath the water. And then there's a water here. Let me just write the magnesium equation in. It's sometimes a little hard to take a screenshot of the whole series and still be able to see things that's happening because of how long the series is. So I'm just going to write the magnesium equation, which this particular screenshot doesn't have, and I'm just going to give you the cell voltage as well. It's just supposed to be negative 2.37, so it's a little bit below water, but yeah, let's assume I've highlighted it in here. What's next? Circle the strongest oxidizing and reducing agent present. There is only one oxidizing agent present, and that's H2O, and the strongest reducing agent present in this case is magnesium. And you can see why you see a reaction, because oh, sorry, another mistake that I have made is I have forgotten to highlight H plus. I was like, hang on, no, the reaction is not between water. So this is why you have to take the question, read the question and take your time and not get distracted by things. All right, so the hydrogen ion is now going to be the strongest oxidizing agent present, and it's going to react with magnesium. And you can see quite a big gap, which generally is an indication that a lot of heat can be formed from the reaction. So you have a spontaneous reaction, and this is where the backward Z can come in handy, because this question doesn't just ask you to confirm that you have a spontaneous reaction, it asks you to write the equations as well. So there is a step 5, which is a little bit tricky because I do have to write this again. So Mg2 plus 2 electrons going to Mg. All right, so let me just do the highlighting again, just so that you can see where what I'm talking about. So there are these two species that I know will react with each other. So there is H plus, and then there is Mg. And if you're going to draw a backward Z, basically you're going to do an arrow in this way, and you're going to do a back arrow down here. So that's how you make your Z. Okay, so like that. My brother came up with another thing. He was like a C. He said, so you can do a C. Actually, a C is probably better, because you can see the direction of how things go. But anyway, just make this shape, whatever you want to call it. And then you should be able to write your equation. So the reduction one, you follow the direction of the arrow. So when you transfer a half equation from the electrochemical series to your work, you will drop the double arrow, because there's only one direction that the equation is going here. So I'm going to just write 2H plus 2 electrons and one direction, so not a double arrow anymore, just one going to H2. So that's the reduction. And the oxidation, I'm going to follow the direction of the arrow as well. So magnesium is going to, so you actually start from the right, magnesium. It's going to go to Mg2 plus and 2 electrons. So you actually essentially reverse this equation so that you can reflect oxidation. And again, there should only be one single arrow in the actual answer. Now the overall, I'm going to add these two together. My electrons are already balanced, so I don't have to do any extra work here. I'm just going to add them. So you have 2H plus magnesium going to hydrogen gas, and this is the hydrogen gas that you see, which gives you the pop test, plus Mg2 plus. And so this is the ionic equation, which you can get just by adding the two half equations from the electrochemical series together. All right, let's try another example of this. The situation here is that you have a solution of hydrogen peroxide which self-decomposes. So hydrogen peroxide will eventually turn into water and oxygen gas. It's a spontaneous process, which is why they normally store it in a duck bottle just to slow down the reaction, because it does get sped up if it's exposed to sunlight. If you want, you can also put it in the fridge, which will slow down the rate of that reaction even further. So if you have a solution of hydrogen peroxide, you essentially have hydrogen peroxide and water. So let's just find water. So there's water, and this is your hydrogen peroxide, and this is hydrogen peroxide. So hydrogen peroxide is very interesting because it can form a spontaneous reaction with itself, and I think you can see that when you highlight and look at the positions of everything, because the strongest oxidizing agent and the strongest oxidizing agent present here. I keep forgetting to highlight water, which is very sad. So there's a water down here, but it's so weak anyway, it's not going to do anything. Um, so H2O2 is the strongest oxidizing agent, and H2O2 is also the strongest reducing agent present. So you can actually form a backward Z just with H2O2. This is why it self-decomposes. And if you connect the strongest oxidizing reducing agent, you're going to see that. So we're going to see how we can go from that to write the half equations. So let me just highlight the species of interest, which is just these two. And so this one undergoes reduction, so it's going to go this way. This one will undergo oxidation, so it's going to go this way. And this is the shape that I want to make, so the arrow will go away from the reactant, of course. So reduction is the first one. It's going to be H2O2. So once you get the hang of this is actually a lot easier than other types of equation, because you just need to copy the half equation that's already been written for you from the electrochemical series. All right, so this one is this one. That's great English, isn't it? This one is this one. And the oxidation, so I need to reverse the second equation. So I have H2O2 aqueous going to oxygen gas, 2H plus, and 2 electrons. So once you add them together, the overall is going to be, so if I just add them, the electrons are already balanced, so I don't have to do anything. And you actually can also cross out the H plus, because it's 2 on the left and then 2 on the right. So the final equation is just 2 H2O2 producing H2O, and there's a 2 here, and oxygens. Okay, so cell decomposition of hydrogen peroxide, which produces water and oxygen gas. That's step 5. I need to remove that. Okay. Um, Another example, hydrogen gas is burned in excess oxygen. So if you list all the species present, you just have hydrogen gas. I feel like I'm going to have to use this oxygen. Let's not talk about this example. This example is a little bit unclear. Okay, so I'm going to remove this example and go straight to example 5, which is another type of question that you can use from the electrochemical series. And essentially, this is using the electrochemical series to predict the operation of a galvanic cell. So a galvanic cell is made from Sn2 plus and Sn and nickel 2 plus and nickel. You need to use the electrochemical series to predict the overall cell reaction, identify the anode, the cathode, determine the direction of electron flow, and calculate the voltage. So the first thing that you're gonna have to do, and I guess you don't have to do it as much because of the way that the learning has been set up, is to draw the galvanic cell yourself. So the first one is made between tin or Sn and tin solution. So probably going to be combined with like nitrate ion or something like that. So you just have what the first half cell is this one. And then the second half cell is made using nickel and in a solution of nickel ion. So you have, let me just write this here. So Sn2 plus, and then this side you have nickel ions. Okay, so if the question asks for a galvanic cell, I normally just set it up and then you have your saw bridge and then you have your wire, and then you can decide which one is the cathode, which one's the anode afterwards. So you're going to have to use the electrochemical series here, and the principle is very similar. You just need to predict the spontaneous reaction that can occur. So I will still list everything that's present, which includes the H2O or the multiple H2O, because these are solutions. You have both, or you have Sn at 2 plus from here, and then you have this Sn2 plus and Sn, and then you also have nickel 2 plus and nickel. Okay, so that's everything that's present. Now if we underline or circle the strongest species, so the strongest oxidizing agent present is Sn2 plus, and the strongest reducing agent present is nickel. So Sn2 plus going to nickel, that's your spontaneous reaction, which means that Sn2 plus is going to undergo reduction to produce Sn, and nickel is going to undergo oxidation to produce nickel ions. Okay, so if Sn is going to undergo reduction, so this is reduction, then Sn must be the cathode, which is side of reduction, which means nickel is the anode. So the flow of electrons is going to be this way. Electrons always flow to the cathode. The overall equation, you just need to add these two half equations together. And so you get Sn2 plus nickel going to Sn and nickel 2 plus. So that's going to be the overall equation. I just add the two half equations together. So predict overall equation, I've done that. Identify anode and cathode, determine direction of electron flow. So the last thing I need to do is to calculate the cell voltage. And in order to find the cell voltage, all you need to do is just find the difference between these two numbers. I don't have enough space, so I'm just going to write cell voltage. So you just need the higher voltage minus the lower. So higher minus lower, which will give you the gap between the two numbers. So in this case is negative 0.14 minus negative 0.25. Your cell voltage has to give you a positive number. Otherwise, it's not a spontaneous redox reaction. So use a calculator if you have to. You should get, in this particular case, 0.11 or 0.11 volt being produced. And that's it. Thank you.